Starting with the graphing part of the review. So there are two types of equations to graph, just like there are two types of equations to solve. We've got exponential equations, which have x as the variable up in the exponent. Now for exponential equations, they have horizontal asymptotes and a domain of all real numbers. Whereas logarithmic functions have a vertical asymptote. Remember, a log, it's like a tree. And in that forest with the tree in it, we're going to have a lion, and that lion is saying, "Roarn." For a range of all real number for the logs. It's easy to get these two mixed up, so just be sure that you know which one has a vertical asymptote and which one has a horizontal one. So we're going to go ahead and take a look at number 2, but I want you to add the following instructions to the top. It says graph the following and state the domain and the range. I also want you to state the transformations and graph the asymptote. Because it's the transformations that let us know where the asymptote is going to be located. So looking at number 2, that 4 on the outside is going to be a vertical stretch by 4, or just V stretch. Don't have to get into super specifics here. The 1/5 is the base. Now, third block asked how we know that that's not the base and not the 4. It's whoever is tied to the exponent. The 1/5 is getting that x plus 3, so that's going to be our base. The plus 3 on the inside with x is going to move us left 3. And then the minus 1, down 1. So if we think of that equation being exponential, what type of asymptote will it have? A horizontal asymptote. So horizontal asymptote that starts going through 0. We vertically stretch it. Nothing. The base doesn't do anything. We move it left 3. Yeah, it's not moving it into a different location either. But if I slide it down 1, that asymptote is now going through negative 1. So now we are ready to make our table of values. The goal with both these and with the logs is once we have it in exponential form, we want the whole exponent to be equal to the power values. So our variable x is up in the exponent. So we're going to want our power values to come from those x inputs. So what could I put in for x so that when I add 3 to it, I get that power value of negative 1? Negative 4. So negative 4 plus 3 is negative 1. Woo! That works. What are we going to plug in for x so that we get 0 up in the exponent? Negative 3. So plug in negative 3. That will give me 0. What can I plug in to get 1 up in that power value? A negative 2. So this is the work that I want to see. What x inputs are you choosing to get to those power values? Now from here, you could use your calculator, or these aren't too bad, you could use PEMDAS to evaluate what the y values would be. But I will say sometimes students will just, whether they use a calculator or do it by hand, they'll forget about that negative 1 or any outside transformation. So just make sure that you are including everything when you are doing your order of operations. So negative 4 in for the x. Negative 4 plus 3 is negative 1. 1/5 to the negative 1 is 5. 5 times 4 is 20. 20 minus 1 is 19. What a great first point that we're not going to graph. So moving on to the next one, we plug in negative 3. Negative 3 plus 3 is 0. What's 1/5 to the 0, or, anything to the 0? 1. Then 1 times 4 is 4, and 4 minus 1 is 3. Next up, we plug in negative 2 for x. Negative 2 plus 3 is 1. 1/5 to the first is 1/5. A fifth times 4 is 4/5. And if I have 4/5 of a pizza and I subtract 1, we have a negative 1/5 of a pizza. And if you were using your calculator, it's totally fine if you have a negative 0.2. Those are the exact same thing. So you can use your calculator or you can do it by hand. But make sure you are including all of those items. Now, the only thing that gets tricky about this as far as transferring your work to the graph is the coordinates that you graph are the x, y coordinates. Those power values are sometimes equal to your x values, but in this case, not. So we have to think about what we are plugging in for x and what we are getting as a final output out for y. Now, as I said, negative 419, it's pretty gross. It's like way up there, so we're not even going to mess with it. Go to our next point. Backwards 3, 1, 2, 3, up 3, 1, 2, 3. Then backwards 2, it's kind of tough to see that negative, but it's there. Backwards 2, and then down a fifth. Right about there-ish. So it looks like we are decaying, getting closer, 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 closer towards that asymptote. Make sure you include arrows on both ends of your graph. So arrows on the function, asymptote shown as a dashed line, table of values clearly shown. Can I check myself on my calculator with that? Sure. Still have to show your work, still have to describe the transformations and draw on that asymptote exactly, but if you are worried about the graphing, not a bad idea to check what it looks like in the y equals part of your calculator. Any questions on the graph part? How about the domain? What's the domain for any exponential? All real numbers, or if you feel like being fancy with parenthetical notation, you can do negative infinity to infinity. The range. Do our y values get covered everywhere? No, they are covered above the asymptote. So y greater than negative 1. So this is the only unit we've had where it's just, oh, I guess not the only unit, our rational functions had greater than as well, where it's greater than and less than instead of greater than or equal to and less than or equal to. All those little details add up to give us one pretty graph. Let's go ahead and skedaddle on down to number 6. Now 6 is a logarithmic function. How do we know? Because you know it has the word log with it. So before we get going, we're still going to describe our transformations first. What's that negative out in front doing? Vertical reflection. The 2, it's just the base. So just like the base doesn't do anything with our exponential functions, base of the log, it doesn't do anything either. Now that minus 3 on the inside is going to move us right 3. So we state the transformations to figure out where our asymptote is going to be. When we see log, we think tree. We've got a vertical asymptote going through 0. We vertically reflect it and flip it upside down. Yeah, it's the same vertical line at 0. The base does nothing. But if I move it right 3, it is going to be in a new location. So a vertical line at 3. Hooray! Now for the less fun part. We see that we have a logarithmic equation. In order for us to make our table of values, we're going to put it in exponential form. Now I'm going to go ahead and sidebar down below here. So I'm just going to go below my graph where I have a bit more room. We've got y equals negative log base 2 of x minus 3. Now, if I try to write this in exponential form, we hit just a slight snag when we do big animal ears because there's one thing that doesn't correspond to big animal or ears, and that is this annoying floating negative out in front of the log. In order for me to put this in exponential form, it has to correspond to every part. Something has to be the base, the answer, and the exponent. So what I'm going to do with that negative is I am going to divide it to the other side. we're going to divide both sides by -1, and that will give me negative y equals log base 2 of x minus 3. So now we have big base 2, animal x minus 3, and ears negative y. So in exponential form, we'll have 2 to the negative y equals x minus 3. Does anyone remember what the last step is before we use this to make our table? We're going to add the 3 over to the other side to make it look as an x equals equation so that it's easier to get those inputs. So 2 to the negative y plus 3 equals x. So folks, I'm going to be looking for the exponential work it requires to write the logarithmic function in exponential form. So I'm going to go ahead, we'll see if I can keep this in view here. What we're going to do is we're going to make our table, and I'm going to write that equation above it. So 2 to the negative y plus 3 equals x. Now from here, it's actually the same thing as what we did with choosing our inputs for exponentials. The only difference is this is not an exponential equation. If you're like, well, look, Mrs. Scott, there's a variable up in the exponent. That is our output variable, so it's still a logarithmic function because the input is in a different spot. So how we go about choosing inputs and outputs, though, is going to be the same as before. We want to get the exponent to be equal to those power values. So -1, 0, and 1. But this time, it's the y values that are going to give us those power values up in the exponent. So what can I plug in for y to give me -1? +1. If I plug in +1 and take the opposite of it, we get -1. What can I plug in for y so that I get 0 in that exponent? 0. What can I plug in so that I get +1 here, a -1? So those are the inputs I'm going to plug in to get those outputs. And now using our calculator, or PEMDAS, we can evaluate. 2 to the -1 will give me 1/2, and 1/2 plus 3 is 3.5. The opposite of 0 is 0. 2 to the 0 is 1, or 2 to the 0 is 1, and 1 plus 3 is 4. Then -1 is +1. 2 to the +1 is 2, and 2 plus 3 is 5. And just like in the problem above, make sure you are pairing this as coordinates with your x inputs and your y outputs. And now we plot the points. So forward 3.5, 1, 2, 3.5, up 1, 4, 0, 5, -1. We are swooshing up towards the asymptote and then going exponentially downward and outward. Our domain will be x greater than what? Our starting x value that we don't actually get to is the location of the asymptote. So x greater than 3. The range, roarn! It goes all the way up and continues going all the way down. So all of those y values are going to get covered. Any questions on the graphing? Raise your hand if this is your least favorite part of the unit, the graphing. Yeah, it's kind of worse than the story problems. So practice these. It's not a bad idea to rework some of the problems in the practice set. Look at your old homework quizzes to see which of those problems you need extra help with. So folks, we're going to go ahead and turn to the second page. And that's it for graphing. And this section of the test, 8.2, it's kind of love it or leave it. Students either do really awesome on this section or they do really poorly. So it's one of those kind of, it's either a 10 or it's a 4 section. So the two things that we need to remember are our rules for going between the two forms, which would be log, big animal, ears, and for exponents, base to the exponent equals the answer. That's what we're going to be using for rewriting between the two forms. For evaluating, folks, how do I evaluate a one log expression? It's the same way we solve a one log expression. It's the same way we graph a log. What do? We put it in exponential form. And that's using our big animal ears. Now, if we start number 13, and we're like, big animal, and then we go, oh, what's our ears? You can just put equals X on the end. And I'm going to prompt you to do that on your test as well. When you are evaluating, just put an equals X on the end, because that's what you're looking for. So that's going to be what your ears corresponds to. So then 3 to the x equals 1/9. At this point, you can either use your mental math skills or you can do what we were doing before the homework quiz and solve this as an exponential. Can I rewrite these as the same base? Sure. 1/9 is the same as 3 to the -2. So x equals -2. Final answer. If you're like, wait, what about checking, Ms. Cairo? Since we're always going to be solving for the exponent here, notice that all of our answer parts of our logs on this section are already greater than 0. Folks, let's go ahead and take a look at number 14. We see one log, big animal ears. What's our big on this problem? It's 10. Don't forget that with common log, when you don't have a base explicitly written, it is automatically base 10. So now 10 is our big, 0.01 is our animal, x is our ears. So 10 to the x equals 0.01. Now at this point, you could just go, I'm gonna go ahead and log both sides, but I'm actually gonna rewrite that decimal as a fraction. And we'll see if it becomes clear what we should do. Folks, can I write 100 as base 10? Sure. 10 squared gives me 100, so 10 to the -2 gives me 1/100. So x equals -2. Hey folks, could I have checked myself on my calculator for this one? Because it is asking us to find the common log of 0.01, which is on our calculator. So you could just use the common log button, 0.01, and what you'll find is that it is indeed -2. We could also do that on the next one, natural log of e, but I want to show you what this one looks like in exponential form. Natural log is the same as log base e of e equals x. So it's kind of confusing because my base is e, but there's also e in the answer part. Big animal ears. And we get e to the x equals e. So what's x equal? Well, if I put that little 1 over there, x is then 1. Alrighty. Expanding and condensing. Make sure you know these rules because, again, this part of the test can either go super right or super wrong. My strategies for remembering what we're trying to do on these problems is expand everything on the land. Expand everything on the land. Yeah, but what does that mean, Ms. Cairo? It means we don't want any exponents. We want everything out in front as a coefficient. Expand also means we want many separate logs So many logs. Whereas with condensing, how many logs do we want? 1. So condensing, 1 log. And our rule for that is send your coefficients to the clouds. Because you can't condense with those coefficients out in front. That was not what I intended to do. Hold on. There we go. So 1 log, send your coefficients to the clouds. Many logs, everything on the land. So to save us a little bit of time, and I'll do this on the test, I think, as well, I'll tell you what we're going to be doing on each of these problems. 16 is expand. 17 is expand. 18 is condense. 19 is condense. 20 is expand. 21 is condense. 22 is condense. 23 is expand. 24 is expand. 25 is condense. 26 is expand. And 27 is condense. If you have 1 log, we want to expand it into many logs. So all the expand ones are already single log expressions, whereas all the ones where we want to condense have multiple logs that we want to put together. So folks, I want you to go ahead and try number 16 and number 19. Give you a couple minutes to try 16 and 19. Let's go ahead and start with number 16. So on this one, we want to expand it into as many separate logs as possible. Folks, I would start this problem from a PEMDAS standpoint and handle that exponent floating outside the parentheses. We are powering up, so let's go ahead and distribute into the exponents that we currently have. So log base 2 of x to the 9th, y to the 3rd. So now we have taken care of the exponent. There are multiple ways you could have done this one. You could have put that 3 out in front of the log first, but I think it's a little bit easier to handle it as part of simplifying first. Next, we want to twist this log apart and expand it into 2 logs. There is multiplication going on in the answer part, so we are going to twist it apart or expand it using addition. So log base 2 of x to the 9th plus log base 2 of y to the 3rd. Most students will get to this point, but a lot will think, oh, I guess I'm just going to stop there. So log base 2 of y to the 3rd. This is where that little mnemonic device comes into play. Expand everything on the land. So we want to take those powers and put them on the land at ground level. So 9 log base 2 of x plus 3 log base 2 of y. Expand everything on the land. Any questions on that one? Moving on to number 19. It's kind of tough to tell, but that 4 is outside these big parentheses. So I would start again from a PEMDAS standpoint and distribute that into all of the logs. On this one, we are condensing. So distributing, we get 4 natural log x plus 8 natural log y minus 4 natural log of z. Before we can condense, we have to send those coefficients to the clouds. So 4 up as a power of the x, 8 up as a power of the y, 4 back up as a power of the z. So natural log of x to the 4th plus natural log of y to the 8th minus natural log of z to the 4th. We have to get rid of our coefficients before we can condense. So now, these two logs are separated by addition. This one has a minus sign in front of it, so I'm going to go ahead and take care of this in one step. We'll have natural log. The addition condenses by multiplying, so x to the 4th times y to the 8th on the top. And then that minus sign means the z to the 4th is going to be in the downstairs. And that's our condensed 1 log expression. See if you can do number 22. So log base 5 of m over n squared. We have to move the coefficient to the clouds first. They are separated by subtraction, and so we condense using division. The last problem that I want to go over on this page is number 23, because this one is a little bit tougher. So in this problem, we have 1 log, and we want to expand it to as many logs as possible. In the answer part, we've got multiplication between the 9 and the x to the 4th. We've got division. And then we've got multiplication going on between the 2 and the y. So I'm going to start by expanding the 9 and the x to the 4th. So log 9 plus common log x to the 4th. But now for this part, folks, I'm dividing by 2 and I'm dividing by the y. So what this means is I'm actually going to have a minus sign in front of each of those corresponding logs. So yes, there is multiplication going on between the 2 and the y, but it's their location of being downstairs, like a negative exponent, that makes both of these subtraction. So sometimes this one throws students off. So from here to fully expand everything on the land, we take that 4 and move it back out in front as a coefficient. So log 9 plus 4 log x minus log 2 minus log y. And that's all I wanted to cover on that page. On the next page, we're going to be crossing off a few problems. I want you to go ahead and cross off number 41, 42, 44, and 45. If you want some challenge problems, you are free to do those, but I won't be explicitly checking them. They can equal decimal. Yep. So folks, on this page, this is the solving submethod. This is the solving stuff like we just did for the homework quiz. So this is the section, make sure you practice. So exponential equations. As we said earlier, for solving, we want to try to get the same bases or log both sides. For log equations, if there's one log, we want to put it in exponential form. If there's two logs, we will either condense or cancel. So pretty much if they're on the same side, you'll condense. Or if they're on a different side, they'll cancel. If there's three logs, you will automatically need to condense the two that are on the same side first. And then you will solve as a two log. So walking through number 31, I just want to see what you guys can do with that as far as trying to get those to be the same base. Here's the perfect sheet. See if you can do number 31. What base can we rewrite those both using? Base 5, 5 to the negative fourth, and 5 to the negative 1. So that's how we give that 5 a bad attitude and send it downstairs. From here, we distribute the power. So negative 1x, negative 8, 5 to the negative 4. We can cancel out our corresponding parts of the 5s. So negative 4 equals negative 1x minus 8. Add the 8, we get 4 equals negative x. So x is equal to negative 4. No need to check for extraneous solutions, but if you wanted to plug it in on your calculator, you would see that you get a true statement. So folks, I think you'll be fine with the rest of those with putting it in exponential form and the like. But on 8.4, I do want you to, on number 48, change the year 2020 to be 2015. So 48, change the year to 2015. And then on the problem above, on number 46, it says the cells are growing at a rate of 9.3% every hour. So our T is going to be in terms of hours. So if we're going to use our exponential model to calculate the number of cells after 1 day, what are we going to plug in for T? 24 for the 24 hours. So just be careful with your units on those. Everything else is pretty straightforward. I will be here after school today if you want to hang out and work on this and ask me questions. I will also be here tomorrow morning at 7:45.